Dear students, we have already learned about the magnetic field of a straight conducting wire, a coil, and also learned about the magnetic force on a conducting wire or a moving charge particle. And then last week, we constructed coils that what we will investigate, meaning that we will study the electromagnetism, meaning that the magnetic field produced by the coils because of the flow of the current in the coil. And we will do two things. Number one, we will experimentally test that fields, and then later on, we will investigate the induction that we have also studies like the Faraday's law or Lenz's law, that how the induction happens. But before that, we also need to do some calculations about our actually last week's constructed coils. The calculations will be mainly the measurements of the magnetic field that what we will be generating with our coils. To understand this, let's start with actually first understanding of produced magnetic field because of a conducting wire. We, for example, have a straight conducting wire, and in this wire, the current is flowing upwards like this I is, and now we can find the direction of the magnetic field produced because of this current using the right hand rule. And if current is upward, then thumb will be upward of the right hand, and the curl of the fingers will indicate the direction of a magnetic flux density B. This magnetic flux density of this wire can be calculated using a formula which is given over here. B is equal to mu naught I divided by 2 pi r, where I is the current which is actually flowing through the current, so through the wire, and r is the position vector, meaning that it is actually the distance at which you are measuring the magnetic field. For example, here this is our r, the distance from this wire. And mu naught is permeability of free space. This is a constant in this formula. So this permeability of free space. So this permeability of free space is a constant value, and its value is 4 times pi times 10 raised to power minus 7 Tesla meter divided by the amperes. So now you can see that this mu naught constant is a pretty small value. So for our given current, then we can see that the magnetic field produced by this wire will be pretty small. So let's raise a question that, for example, we want to generate magnetic field because of this straight wire of the order of zero point 0.1 Tesla, like 0.1 Tesla. So 0.1 Tesla I selected because normally when you buy the magnetic materials from the market, their magnetic field of zero point 0.1 is easier to achieve. So then now if our magnetic field is 0.1 and we want to calculate this magnetic field at a distance of 1 centimeter from a wire which has a current I. Now we can rearrange this formula for the current. Then our current I will be equal to B times 2 pi r divided by, so 2 pi r divided by mu naught. So now we can simplify this, that 2 pi r times b divided by 4 pi times 10 raised to power minus 7, the value of permeability. So pi cancelled with pi and 2 will make it 2. Then now our formula is magnetic flux density B times R divided by 2 times 10 power minus 7. So this is minus 7, sorry. So now we can put these values over here, that B, that what we want to generate is 0.1 Tesla. Tesla is the units of magnetic flux density, and R is a 1 centimeter. It means it is a 1 into 10 raised to power negative 2 divided by 2 into 10 raised to power minus 7. This minus 7 on the numerator, it will be positive 7, and there is a negative 3. So that will be equal to 5 times 10 raised to power 3 amperes. So you see that here, just to generate only 0.1 Tesla magnetic field, why this wire you need 5,000 amperes of current, which is a very, very large value of the current. So it means that this will not be easier to produce such a strong magnetic field using a simple wire and flowing the current through it, because this large current will melt down this wire because of Joule heating. Now we can try to understand the magnetic field produced because of a coil. How would it produce? This we have already understood, and now we will try to do some calculations for the coils as following. Okay, so now we can consider that we do have a coil, meaning this is a solenoid, and this coil has a length of L, and the number of the turns in this coil are capital N. So that means that these are total number of turns in the coil. Total number of turns. Okay. And I is the current which is flowing through this coil that we have applied. So the magnetic field generated because of this coil can be calculated using a formula, that is a B is equal to mu naught, which is a permeability of free space 4 pi 10 raised to power minus 7 Tesla meter per amperes, times N, the total number of turns, times I, the current, and then divided by the length of this coil. Now, let's consider that we have constructed our coil, and we constructed our coil with, let's say that the L is equal to half a centimeter. So we put our all number of turns in just within half centimeter. And then the number of turns that we used, let's say we have 200 turns, and we want to produce the magnetic field. Again, we can consider that it is 0.1 Tesla. Now, what we can do, we can calculate that how much current do we need to flow through this coil. So Here we can again rearrange our formula. So I is equal to B magnetic flux density times L length of the coil divided by mu naught, which is the constant permeability of free space, times N number of turns. Now we can do these simple calculations that B is zero point 0.1. The length of the coil is half 0.1 into 10 raised to power minus 2 divided by 4 pi times 10 power minus 7 times 200. So now we can find that what the current that we need to generate this uh, magnetic field. So let's do a simple calculations. That is equal to about 2 amperes. So this 2 amperes current is not really a very large current. So it is still actually a significantly big number in terms of the current. But how we can actually estimate that either this current is really a large current or the lower current? So for that, we need to check that how much the heat will dissipate if we give this much current to our coil. How we can do the calculations for the heat dissipation? For that, we need to use the power formula. Let's also do that calculations. To calculate the power dissipation, we need to do the following. Okay, to do the power dissipation by this coil, we need to use the power formula, which is P is equal to I square R. Here, I is the current that we are giving to the coil, and R is the resistance of this coil. That you can also measure using your multimeter, but we can also calculate it using this actually the formula of the resistivity, meaning that the resistance is equal to resistivity of the wire times length of the wire divided by the cross-sectional area. And we are using the copper wires for our coils. So then the resistivity of the coil at room temperature is a 1.68 into 10 raised to power minus 4 ohm meter. And the length of the wire, to calculate the length of the wire, we need to actually use the formula 2 pi r times the number of turns, because 2 pi r is the length of one turn and n are the total number of turns. So then the total length is 2 times 3.14, and let's say that the radius of our coil is approximately 3 centimeters. So 3 into 10 raised to power minus 2 and times 200 turns that we use. So these two zeros are going with this one. This is 12. So this is going to be approximately 37 ohm. So this is approximately the resistance of our this coil. Now the power dissipation P is I square R, the I current which we actually give to this coil is 2 to 2 square is a 4 times 37, which is the resistance of this wire. So now we can see here. So this is 148 watts. That is the power. Now you can see that your coil with 200 tons within half centimeter, when you actually will give the current of 2 amperes, it will dissipate the heat, which is actually equivalent to 148 watts, meaning every second you are dissipating 148 joules of the energy. And this is actually a quite significant amount of the thermal energy. So that could not be good for your coil. So you need to actually keep your coil at low temperature or in the water bath in this condition. Or you need to actually redesign your coil. And how you should redesign your coil, this is what the project that you need to do. That, for example, you can increase the number of turns to reduce your current required to generate, let's say, zero point 0.1 Tesla magnetic field. Or you can say that if, for example, we lower the limit of our produced magnetic field down to zero point zero 0.05 Tesla, then that will also be quite good number, and that will be quite good number to do the measurements, because our detector will be really very sensitive and it can actually measure even a smaller magnetic field. So now this is actually up to you guys, that now you know that how to do the calculations for the magnetic field, for the resistance of your coil, and these all numbers you must have before designing your final coil, that what you will use for electromagnetic induction. Thank you very much. Hope you actually understood it. If you have any question, you can leave it in the comments section, and we will keep our discussions in coming lessons. Thank you very much.